When most people imagine Native American homes, they picture teepees rising across the plains, or towering longhouses in dense forests. But beneath the surface, literally, lies a chapter of architectural brilliance few ever hear about. Imagine stepping into a home carved partly into the earth, where the outside world might be blistering hot or dangerously cold, yet the interior stays calm, steady, and remarkably comfortable. No electricity, no furnace, no air conditioning, just physics mastered long before the word existed. Across North America, ancient Native American communities built underground and semi-subterranean shelters that harnessed the stable temperature of the earth itself. Buried walls absorbed the heat of summer and released it slowly in winter. Thick earthen roofs protected against scorching sunlight and freezing winds. Ventilation shafts created natural convection currents that maintained fresh air without dramatic heat loss. These weren't primitive holes in the ground. They were thermal machines, engineered with precision and refined over generations. In winter, families warmed themselves with only a small fire, the earth around them acting as a colossal heat battery. In summer, while the outside world baked, these homes felt cool and refreshing, insulated from extreme temperatures by natural thermal mass. Some even incorporated angled entrances to direct airflow, central pits for capturing warm or cool air, and carefully placed hearths that turned the entire structure into a climate-regulated cocoon. Today, we spend fortunes heating and cooling our homes, yet ancient builders achieved equilibrium using nothing more than soil, stone, timber, and an extraordinary understanding of how the earth breathes. If you're ready to discover the hidden engineering that makes modern architecture look wasteful by comparison, hit subscribe. And let's step underground into a world where survival met innovation, and the environment itself became part of the home. Human eyes are drawn to what rises above the ground. Towering structures, decorated walls, dramatic silhouettes. But some of the most impressive engineering in Native American history took place below the surface, where architects shaped the earth itself into a living shelter. These underground and semi-subterranean dwellings are often overshadowed by the teepee, hogan, or longhouse in popular imagination. Yet for thousands of years, they formed the backbone of winter survival and stable year-round living in countless regions across North America. Archaeologists often describe these homes as pit houses, earth lodges, or semi-subterranean dwellings. But those labels barely capture their sophistication. People didn't dig simply to hide from the cold. They dug because the earth offered a powerful natural advantage: thermal stability. Unlike surface air, which changes temperature dramatically with the seasons, soil just a few feet down remains remarkably constant. Winter might rage above, summer might scorch the plains, but the temperature under the ground shifts slowly, providing a naturally regulated environment. By sinking their floors into the earth and using the excavated soil to build up thick, protective walls, ancient builders tapped into this stable microclimate. Inside, temperatures were dramatically more comfortable than the outside world, warm during freezing winters and cool during blazing summers. But these shelters weren't only practical. They reflected a worldview deeply attuned to the land. The earth wasn't a barrier, it was a collaborator. Every curve of the wall, every placement of a post, every angle of an entry tunnel was shaped by generations of accumulated knowledge about how heat moves, how winds shift, and how a home breathes. This section peels back the surface, literally, to reveal a forgotten layer of architecture where survival, engineering, and environmental intelligence merged into a single, enduring tradition. To appreciate the brilliance of underground Native American shelters, you must first understand their silent partner, the earth itself. Soil is not just dirt. It is one of the most effective natural insulators on the planet. A few feet below the surface, temperatures remain surprisingly stable year-round, protected from the chaos of weather, storms, and seasonal extremes. In many regions of North America, the ground beneath the frost line holds steady around 50 to 55 degrees Fahrenheit, 10 to 13 degrees Celsius. That means a winter night dropping to minus 20 degrees Fahrenheit or a summer afternoon rising above 100 degrees Fahrenheit still leaves the subsurface largely unchanged. Ancient builders recognized this, not through thermometers, but through observation, experience, and generations of experimentation. By placing a home partially underground, they created a dwelling anchored to this stable thermal zone. The earth surrounding the walls absorbed heat slowly and released it slowly, acting like a massive thermal battery. In winter, the soil shielded the home from freezing winds while trapping warmth from body heat, cooking fires, and radiant heat from packed earth floors. In summer, the same soil absorbed the day's heat before it could enter the living space, creating a cool, comfortable interior even in scorching climates. Builders also understood how different soils behaved. Sandy soils drained water quickly and prevented dampness. Clay-heavy soils held heat more effectively. Rocky ground demanded reinforced structural posts but provided excellent thermal mass. Every building decision, depth, wall thickness, material choice, emerged from reading the land. This wasn't accidental architecture. It was a deliberate choice to make the planet itself part of the shelter. In a world with no electricity and no manufactured insulation, Native American communities tapped into a resource modern architects are only now returning to: the earth as an engineered climate control system, consistent, reliable, and endlessly renewable. Digging into the earth was only the beginning. What transformed a simple pit into a fully functioning home was design, intentional, tested, refined. Ancient Native American underground shelters followed architectural rules that balanced stability, airflow, strength, and long-term comfort. These principles weren't written down. They were inherited through generations of building, rebuilding, and observing how structures behaved through storms and seasons. The first rule: depth matters. Builders dug just deep enough to reach the stable thermal zone, but not so deep that moisture collected in the floor. This sweet spot varied from region to region, and families knew it by testing the soil temperature, drainage patterns, and frost depth each year. The second rule: the chamber must rise above the entrance. The entry passage, sometimes a sloped ramp, sometimes a tunnel, always sat lower than the central living area. This deliberate elevation created a natural cold trap. Dense, cold air settled near the entrance while warmth collected in the raised chamber. No doors, no insulation panels, just physics used with precision. Next came the roof structure, often one of the most impressive elements. Builders placed sturdy wooden posts in a circular or square arrangement, then laid crossbeams, rafters, and finally thick layers of brush, sod, and packed earth. This roof acted like a heavy protective shell, merging the home seamlessly into the landscape. Inside, the beams provided strength, while the earthen covering offered unparalleled insulation, reinforcing the natural temperature stability of the underground chamber. Finally, interior layout mattered. Sleeping platforms were raised and placed along the edges, where temperatures were warmest. The central area remained open for movement, tool-making, and fire use. Storage pits were carved into the floor, where cooler air preserved food through the winter months. Nothing in these shelters was random. Every line, slope, and layer served a purpose, turning a hollow in the ground into an enduring, climate-controlled home. During winter, the outside world could be brutal. Freezing winds, deep snow, and temperatures that threatened survival. Yet, inside an underground Native American dwelling, the air often felt still, calm, and remarkably warm. No modern insulation, no metal stoves, sometimes not even a large fire. So, how did these homes retain heat so effectively? It begins with thermal mass, the ability of materials like earth, stone, and thick timber to absorb heat slowly and release it gradually. Once warm, these materials acted like a thermal reservoir. Even a small fire, or the combined body heat of a family, could warm the interior enough to raise the temperature significantly above the freezing conditions outside. The earth surrounding the walls insulated that warmth, preventing rapid heat loss. The heart of winter heating came from a carefully managed central hearth. Builders placed the fire directly beneath a controlled smoke vent, usually at the roof's apex. This vent wasn't a simple hole, it was an engineered system. Its size, shape, and angle determined how smoke left the chamber and how heat remained inside. A too large vent wasted precious warmth. A too small vent risked smoke buildup. Finding the perfect balance required skill and constant awareness. Fires in these homes were low, steady, and slow-burning, unlike the roaring flames often used in surface dwellings. The goal wasn't brightness, it was endurance. A bed of glowing embers could radiate heat for hours, soaking into the earthen walls and maintaining a stable temperature long after the fire dimmed. Warm air naturally rose to the upper parts of the chamber, where sleeping platforms and resting areas were located. Cold air sank toward the lower entrance tunnel, staying away from living spaces. This natural convection pattern created a layered environment of warmth without 1 ounce of modern technology. During the coldest seasons, these homes weren't just shelters. They were thermal machines, capturing, storing, and reusing every bit of heat the household produced. If winter showcased the warming power of earth-sheltered homes, summer revealed their second astonishing secret. They stayed naturally cool, even when temperatures outside soared. This wasn't accidental. It was the direct result of design choices that turned underground dwellings into some of the most effective passive cooling systems ever created. Above ground, summer heat rises, radiates off surfaces, and gets trapped inside enclosed structures. Underground, the story changes entirely. Soil absorbs heat slowly. Even after days of intense sunlight, temperatures just a few feet below the surface remain steady and cool. Ancient builders understood this long before modern geology explained why. By placing their living spaces partially or fully underground, Native American families enjoyed temperatures far lower than the sweltering conditions outside. The thick earthen roof acted like a massive shade canopy, blocking sunlight and preventing thermal buildup. The surrounding soil absorbed heat from the interior, keeping the chamber comfortable throughout the day. But cooling came from more than soil alone. It relied on airflow engineering. Flushing shafts created a natural stack effect. Warm air inside the chamber rose toward the vent and escaped. Meanwhile, cooler air from the lower entrance tunnel flowed inward to replace it. As long as temperature differences existed between the inside and outside air, this self-regulating cycle continued on its own, requiring no manual adjustments or modern equipment. Interior features reinforced the cooling system. Storage pits remained cold year-round, making them ideal for preserving food during hot months. Sleeping platforms were placed along the sides of the chamber, where air circulation kept temperatures pleasant. Fire use was minimized or shifted outdoors during the summer, preventing unnecessary heat buildup. To modern architects, these homes appear astonishingly efficient. To the people who built them, this was simply how a home should work. In harmony with the land. Using physics, the earth provides freely. One of the most misunderstood challenges of underground architecture is air quality. Without proper airflow, an enclosed earth chamber can become stale, smoky, or dangerously low in oxygen. Yet Native American underground shelters avoided these problems with a sophistication that stuns modern engineers. They created ventilation systems that worked day and night, in silence, without tools, without mechanical parts, and without wasting heat. The genius of these systems lay in how builders shaped air pressure and elevation inside the home. Every underground dwelling relied on 2 openings: a lower entrance, placed near ground level or at the bottom of a sloped tunnel, an upper vent, cut into the roof at the highest interior point. This vertical separation was deliberate. Warm air rises, pulling cooler air behind it. As heat collected inside the chamber, from people, cooking, or the earth itself, it created a gentle upward current that pushed stale air out through the vent. Meanwhile, the cooler, denser outside air slid through the lower entrance, replacing what escaped. The result was a continuous, self-sustaining airflow cycle that kept the interior fresh without letting warmth escape rapidly. Vent openings were not fixed. Builders adjusted them depending on season and weather. In winter, the vent was narrowed to preserve heat while still releasing smoke. In summer, widening the opening increased airflow, enhancing natural cooling. These adjustments required awareness, understanding how wind, temperature, and fire behavior interacted inside the shelter. Some regions developed even more advanced features. Side vents carved into the roof mounds helped redirect wind. Entry tunnels angled against prevailing gusts prevented sudden cold drafts. Interior partitions guided airflow around the chamber, preventing stagnant pockets of air. This wasn't primitive ventilation. It was precision air management, refined through centuries of lived experience. In the darkness of an underground home, air didn't sit still. It moved with purpose. What made these underground shelters truly remarkable wasn't just that they were dug into the earth. It was how every layer of the structure worked together to stabilize temperature, resist weather, and create comfort. These homes were not simple pits. They were constructed as multi-layered thermal systems, each component contributing to the overall climate control strategy. Start with the floor, carved into stable soil that stayed cool year-round. Builders understood that cold air settles low, so the very center of the living chamber was slightly elevated compared to the entrance tunnel. This subtle rise created a warm zone where daily life could unfold comfortably, leaving colder air trapped near the entry. Some floors were lined with packed clay or wooden planks to reduce moisture, while others incorporated heated stones during winter to radiate warmth upward. Next came the walls, reinforced with wood, brush, or woven plant materials, before being coated with layers of earth. These walls acted like thick thermal blankets. Earth absorbs heat slowly, meaning the interior temperature changed gradually rather than fluctuating with every shift in outdoor weather. In summer, the walls pulled warmth out of the room. In winter, they released stored heat back into the space. Then there was the roof, arguably the most advanced element. It was built in layers, a frame of wooden beams arranged in a radial pattern, topped with brush or grass mats, then covered with thick sod or packed soil. This roof wasn't just protection from above, it was a thermal shield. The heavy earthen layer blocked sunlight, resisted wind, and added immense insulation, while the sloped design prevented rain or melting snow from pooling and causing leaks. Walls, floors, roofs, each worked with the others. Together, they created a living environment where temperature stayed steady, breathable, and survivable in all seasons. This was architecture designed not to fight nature, but to work with it. What was it like to live inside these underground dwellings day after day? Far from the dark, cramped image many people imagine, these spaces were organized, warm, efficient, and deeply connected to the rhythms of community life. Step inside, and the first thing you notice is the quiet. The earth absorbs sound, muffling storms, wind, and outside noise. For families who endured harsh winters or scorching summers, this natural silence offered comfort and stability. The interior was divided into functional zones. The central area, closest to the hearth, was the warmest spot, ideal for cooking, tool-making, storytelling, or winter craftwork. Around the perimeter, raised sleeping platforms kept individuals above the coldest air while maximizing the gentle heat rising from the fire. Storage pits, dug into the cool earth, preserved seeds, dried foods, and valuables long-term, taking advantage of the underground's natural refrigeration. Daily routines revolved around temperature management. At sunrise, someone tended the fire, adjusting the vent to maintain draft without letting heat escape unnecessarily. During winter, people warmed stones in the hearth, placing them near bedding or under mats. During summer, interior fires were rare. Tasks often shifted outdoors to keep the home cool. Air quality required constant mindfulness. If smoke lingered too long near the ceiling, the vent was widened. If cold drafts swept in, entry coverings were repositioned. These actions became part of the natural rhythm of daily life, as instinctive as adjusting a thermostat today. Far from primitive, these homes supported complex social interactions. Families shared meals, elders taught skills, children learned responsibilities, and the shelter itself became a space of continuity. The structure wasn't merely a refuge from weather. It was the center of community, a stable ground where memories, lessons, and traditions were built. In a world of extremes, these underground homes offered peace, physically, emotionally, and socially. Beyond climate control, underground shelters offered another powerful advantage: protection. In regions where winter storms, predators, rival groups, or environmental hazards threatened daily life, a home partially hidden beneath the earth provided natural security that surface dwellings could never match. First, these homes excelled in weather defense. A blizzard that could rip apart a teepee or collapse a poorly built surface shelter posed little threat to a semi-subterranean dwelling. Its walls were reinforced by the surrounding soil. Its roof was supported by heavy timbers capable of bearing immense weight. Even hurricane-strength winds skimmed harmlessly above the low-profile mound. Fire protection also improved underground. A controlled hearth in a pit house was far less likely to ignite grasslands or forest brush. The thick earthen roof created a buffer that contained sparks and embers, adding a layer of safety in fire-prone regions. Then came the advantage of camouflage. From a distance, an earth-sheltered home blended seamlessly into the landscape. In open plains or desert regions, this meant reduced visibility to potential enemies or roaming animals. A village of partially underground dwellings could appear as natural rises in the land rather than human settlements, a crucial factor during unstable periods in history. The underground offered acoustic protection too. Sod and soil absorbed sound, muffling conversations, footsteps, and daily activity. Even large gatherings generated less noise than surface structures, a remarkable asset when groups needed to remain undetected or avoid attracting predators. These dwellings also stood the test of longevity. While hide coverings or bark walls required regular replacement, the earth walls and floors remained stable for years with only moderate maintenance. In many archaeological sites today, their outlines survive long after wooden and woven structures have vanished. In choosing to build downward instead of upward, Native American communities gained a fortress, one shaped by the land, sustained by the land, and protected by it. As modern society battles rising energy costs, extreme weather events, and the urgent need for sustainable building practices, a surprising truth emerges. Ancient Native American underground shelters solved many of these challenges thousands of years ago. Their design wasn't a relic of the past. It was a demonstration of what architecture can achieve when it listens to the environment instead of overpowering it. Underground dwellings offer a radically different perspective on what a home can be. They prove that comfort doesn't require constant mechanical heating or cooling. Instead, stability can come from thermal mass, from shaping a shelter to match the land, from working with natural airflow patterns. These principles are the foundations of modern passive house design, earthships, and eco-shelters. Yet indigenous builders mastered them before the first written manuals on architecture existed. The earth itself is the blueprint. Stable temperature, natural soundproofing, fire resistance, energy efficiency, longevity, low environmental impact. Today, architects revisit ideas like bermed earth homes, sunken living spaces, green roofs, and underground insulation systems. But these aren't new inventions. They are rediscoveries of ancient wisdom refined over centuries of observation, adaptation, and experimentation. Underground shelters also challenge our assumptions about indigenous innovation. The narrative that pre-contact Native American dwellings were simplistic collapses when faced with the engineering precision of these structures. They weren't temporary fixes. They were sophisticated climate-responsive systems built with a deep understanding of physics and ecology. As we move into a future shaped by climate extremes, these old designs offer new direction. They invite us to imagine a world where architecture doesn't strain against nature, but harmonizes with it, providing comfort without excess energy, stability without waste, and resilience without massive infrastructure. The ancient earth shelters were more than homes. They were lessons, ones we are only now beginning to relearn.